Welcome to Maths with EJD. I'm still talking about basic calculus, and I've made 3 videos before now. This will be, I think, the last video on differentiation actually. It will be like the eighth on basic calculus. We still have application of differentiation and integration and its application to go. So, but this is like the fourth video on differentiation in particular, and like the last video on actual differentiation, apart from the application that we'll be talking about in subsequent videos. So, of course, I'll be talking about different techniques of differentiation with different kinds of functions. So now my attention is shifting to implicit functions. In the videos about types of functions, I told you about implicit functions, that they are functions where you cannot make y the subject of formula explicitly. You cannot write y is equal to something so that every other thing on the right-hand side is f of x. So they are functions such that when you write y, you still have f of x and y together on the right-hand side. So that's why they are implicit. So everything is joined together. You cannot separate y from x. That's what that is. So, and how do you deal with implicit functions? First of all, you need to understand, you must know that dy dx, you know that d dx of f of x is the same thing as f prime of x settled. And then in this case of implicit functions, you're going to come across problems with y. So if you have d dx such that y is involved, you have f of y. So that has to be, since you're looking for d dx of f of y, so you cannot differentiate y with respect to x in that sense. So what you have to do is you have to break it down, and you have d dy of f of y multiplied by dy dx, so that dy can cancel out. So it's still your d dx that you have. So, but d dy is appropriate to take care of f of y. And then at the end of the day, d dy f of y is f prime of y multiplied by dy dx. So dy dx is what balances out the situation like that. So let's see examples like that. Let's say you have equation of a circle starting from the origin. For instance, if x squared plus y squared equals r squared, this is the equation of a circle starting from the origin, like this kind of circle that the circle with radius r, that is, so this is radius r now. So it's x squared plus y squared equals r squared. Find dy dx. So you can see here, of course, we can make y the subject of formula for sure with square roots on the other side, but we can treat it as implicit, right? So here, what you just do is you have ddx of x squared plus ddx of y squared. You see ddx of y squared, that's not done, right? Because this is y. And you have ddx of r squared. R squared is constant here, so don't worry. It's a constant, so it will go to 0 normally. So ddx of x squared is easy. That's just 2x. But then you cannot find ddx of y squared like that. So you have to do ddy of y squared multiplied by dy dx to balance it out so that it will still be same ddx that you are looking for originally. Okay, so you have d, instead of d dx of y squared, you now have dy of y squared multiplied by dy dx. And dy of y squared is still 2y. That's when you differentiate y squared, you get 2y with respect to y now. And then dy dx here is here to balance it out. And that is exactly what we are looking for when we differentiate. And this, since radius is constant, so d dx of r squared is 0, and then all you have left is so you can transfer 2x to the other side. That's minus 2x. So you have 2y dy dx equals minus 2x. And then dy dx is what you're looking for. So you have to divide both sides by 2y like this, 2y. So this cancels out. So you have dy dx. So you have dy dx equals minus 2x minus 2y. So 2 cancels out. So you have minus x over y. So the derivative of the equation of a circle passing through the origin is actually minus x over y, basically. Okay? So that's a very simple application of implicit functions. All right. So let's take another example. So here we have find dy dx for xy plus sine xy equals 4 minus x plus y. So again, you have ddx of xy. This x and y has both x and y. So you have to find ddx and ddy together. So you have ddx of xy, and you now find ddy of xy dy dx to take care of the y part. So this one takes care of the x part, this one takes care of the y part. And then when you come here, you have ddx of sine x again, and then you have ddy sine xy to take care of the y part, dy dx. Whenever you take care of the y part, dy dx is there to balance it out, just like you see dy dx cancel. So you still have your ddx technically. and then this is 4, d dx of 4, 4 is constant, and minus d dx of x plus this is y standing on 2. So you have d dy of y, dy dx, basically. And then d dx of xy, that means you are differentiating xy with respect to x. So in that case, x is the focus, so y is constant, so y remains. Then d dy of xy dy dx. So that's, you are differentiating xy with respect to y. So x will remain, because in that case, x is like constant, but then this is balancing it out, dy dx. So you have y plus x dy dx plus, then when you come here, you want to differentiate sine xy with respect to x. Sine xy with respect to x, that first of all, differentiate xy with respect to x, you get y, and then differentiate sine, you get cos, xy now remains. Then here, same thing, but except that the focus is now on y. So differentiate sine xy with respect to y. So differentiate xy with respect to y, that will give you x, and you have cos xy. But that's to be balanced with dy dx, because you are differentiating y there. And then differentiate 4, which is constant, that's 0. Differentiate x, you have 1. And then d dy of y, that's 1 normally. Then you have dy dx balancing it up. So the next thing you're doing is to collect all the dx together. So this, anything dx, bring them together, because that's what you're looking for at the end of the day. And then other things, you put them together. So you have this one now is what you have here. Then this is the y here. And then y cos xy, anything that doesn't have dy dx, I brought them to the left hand side, and on the right hand side I have dy dx. This comes here, then minus x dy dx. This one is what has come here, and then x cos xy dy dx has come here now, so that you can have all of that on one side. So you have 1 plus y cos xy equals, factorize the x dy dx now. So if you factorize the y dx, you have 1 left here, you have minus x left here, you have minus x cos y left here, and then dy dx is outside. So you can now divide through by this expression, so you can have dy dx alone. So dy dx is actually 1 plus y cos xy all over 1 minus x cos xy. And that is the result of that. So you just have to be careful. Anytime you differentiate with respect to y, you just know that a dy dx ends up being there to take care of that. So that's slide 35. Let's come to slide 36 now. Okay, yeah, that's the end of implicit functions, and that's just how to go about it. So that takes us to logarithmic functions. How do you differentiate logarithmic functions? So now I told you under types of functions that there are 2 types of logarithms. You have log to base e, which is natural logarithm lean, or Napierian logarithm, and you have log to base 10, which is just written as log most times. So most times in science, we just use natural logarithm, right? So this is natural, this is common. So whether natural or common, the idea is basically the same. So if you have y equals ln f of x, then dy dx will simply be differentiate the function f of x and put it over the original function you had before, right? So you have f prime of x all over the original f of x, like that. So that's for logarithmic function. So, and this, it has a proof, right? It has a proof. So imagine that y is equal to ln f of x. So if you take, we talked about inverse of functions, right? The inverse of log is exponent. The inverse of exponent is log. Just like the inverse of square is square root. The inverse of square root is square, something like that. So to take care of this ln now, you can raise both sides to power e. So you have e raised power y, e raised power ln f of x. And whenever you have e raised power ln anything, so the final result is this x in front of it, because e cancels ln, so x comes down. So e cancels ln and f of x settles. So you have e raised power y equals f of x. Okay. And then as you have e raised power y equals f of x, the next thing is you now want to differentiate with respect to x. So you have d dx of e raised power y and d dx of f of x. So since this is y here, there's no x here, so you have to now say d dy of e raised power y dy dx, and then that is equal to d dx of f of x. So d dy of e raised power y, when you differentiate an exponential function, it remains the same. D dy of e raised power y is still e raised power y, but and then you have this dy dx. That's why you have this. And d dx of f of x is f prime of x. So you get this now. So you now have dy dx equals f prime of x all over e raised power y. And don't forget, e raised power y is the same thing as f of x. So that means that dy dx is f prime of x all over f of x. So that's the proof for y, whenever you differentiate a logarithmic function, it is the derivative of the function in front of the log over the original expression. So that takes us to an example like this. You have example 1. For f of x equals ln x squared plus 5x plus 2. Find f prime of x. That's easy. F of x is ln x squared plus 5x plus 2. So f prime of x will just be d dx of x squared plus 5x plus 2. That's differentiate that. Put it over the original. So you have differentiate this now. You have 2x plus 5 all over the original thing. And then that is your result. It's so pretty easy. And then to make things a bit more complicated, not so difficult. So you have to find y dx if y is equal to ln square root of x squared plus 1. So here again, you have y equals ln square root of x squared plus 1, which is better seen as ln x squared plus 1 raised to power half. So you have dy dx equals d dx of x squared plus 1 raised to power half. This is like function of a function, and I've told you the secret for that. The secret is this power, bring it down, differentiate inside, that's 2x. Keep the original thing, but the power is now reduced by 1. So half minus 1 is minus half. So, and then you have 2 canceling 2 here. So you have x there. So you have x into x squared plus 1 raised to minus half. Interestingly, this is also x squared raised to half. So you can actually bring this up. So this is more like you have x times x squared plus 1 raised to power minus half. And then if you also take this up, it's another minus half, you know. So that's why at the end of the day, it's x into x squared plus 1 raised to power minus 1. And then that's more like x over x squared plus 1. So when you differentiate that logarithmic expression, this is what you get. So that's a logarithmic expression. Okay, I mean, things are moving so fast these days. So once you know the principle, it's easy. Just logarithmic expression, differentiate the function and put it over the original function, and that's all. And you saw the proof right there. So this is exponential functions now, which is like the inverse of logarithmic functions. And, you know, if you have y equals e raised to power f of x, so what makes it exponential is this e that is carrying the function on its head. So it will simply just be differentiate the function f of x and multiply by the original expression e raised to power f of x. So dy dx equals f prime of x e raised to power f of x. So differentiate this function and multiply by this original function. So you have f prime of x e raised to power f of x. That's a simple rule for exponential functions. So let's see. Okay, this is slide 40. So it means that the next one would be 41 right here. Okay, so now we are trying to prove that it is actually correct, just like we proved for log. So you have y equals e raised to power f of x, right? And of course, if you want to humble e, you have to use log. That's a natural log. So take the ln of both sides, like I like to say. So that's ln y, ln e raised to power f of x. So, and of course, you know, ln will cancel e. So this will just be ln y equals f of x. And then you have already learned about implicit functions, right? So ln y is like an implicit function. So divide both sides. So you have d dx of ln y, d dx of f of x. So of course, since this is y, you have to say d dy ln y times dy dx to balance out. So it's still more like d dx of ln y technically. So you have d dy ln y dy dx equals d dx of f of x. So, and of course, we just did ln y. Now, if you differentiate ln y, that means differentiate y with respect to y, that's 1. Put it over the original y, that's 1 over y, and you have dy dx right here. And then d dx of f of x is f prime of x. So then you can multiply both sides by y, so that this y can go. So y times this and y times this. So this cancels out. So you have dy dx equals y times f prime of x. And again, remember, y here is e raised to power f of x. So it means that dy dx is basically f prime of x times e raised to power f of x. Easy proof right there. Easy proof. And then you can go to the next one where we take some examples. So you have to find f prime of x. If f of x is e raised to power sine x plus ln 1 over x. You know some complications right there. So you have f of x equals e raised to power sine x plus ln 1 over x. And that's the same thing as e raised to power sine x plus ln 1 over x is the same thing as x raised to power minus 1. And then that means to differentiate that, we just have f prime of x equals d dx of that whole expression. You know, this is more like the expression there. So d dx of sine x plus ln x raised to power minus 1 times the original expression, right? And then differentiate sine x, you get cos x. Then to differentiate ln x raised power minus 1, that means differentiate x raised power minus 1, x raised power minus 1. To differentiate that means bring down the power, that's minus 1 times x raised power minus 1 times minus 1. Minus 1 times minus 1, that's minus 2. So you have minus x raised power minus 2 all over x raised power minus 1, the original expression. That's how we deal with log. And then you have this original thing, this original expression there, e raised power of that, And then what we are doing here is just to tidy things up. So you have cos x. So because of this minus, now minus times plus, this becomes minus. And then you can take this down because it's like x raised power minus 2. So it goes down, becomes x raised power 2. And this x raised power minus 1 was down here before. So you have x raised power minus 2 times x raised power 2. That's x raised power minus 1 plus 2. That's x raised power 1. As you can see here, x raised power 1. So lastly, you have cos x minus 1 over x raised power sine x plus ln x raised power minus 1 is still ln 1 over x. And that's how that goes. That's how that goes. So it's a bit tricky, but you just have to pay attention to the fine details right there. Okay. So we take another example, still under exponential functions. You have what is dy dx if y is equal to e raised power square root of x squared plus 1. You can see that I've been coming along with this root x squared plus 1. I've been doing a lot of things with it. I don't know. I mean, I just like I'm just enjoying using that. So you have y equals e raised power root x squared plus 1. That's like e raised power x squared plus 1 raised power half. So dy dx will simply be d dx of that expression at the top multiplied by the original thing you have. So again, I've told you, bring down the power, that's half, differentiate inside as 2x, then keep the original thing, that's x squared plus 1 raised power minus half, times all this. And then all you just need to do is tidy things up. So you have x all over this, x over this, but then you have this e again here. So, and again, what do? We just write it out like x over root x squared plus 1, e raised power root x squared plus 1, because we cannot simplify beyond that. So just know the rules and apply them. That's what this is all about. So we go to special cases of exponential function. We're dealing with exponential functions. Y equals 2 raised power x is an exponential function, for instance. So how do we differentiate that? So to differentiate it, first of all, you want to bring down the x. And of course, whenever you have any power like this, you can use ln. So you have ln y equals ln 2x. And from the laws of indices, x can come down. Indices are logarithm, so x can come down. So you have ln y equals x ln 2. The next thing, you can differentiate both sides. So you have d dx ln y, d dx times x ln 2, right? And d dx ln y cannot go straight, so you have to do d dy ln y multiplied by dy dx. And then you have d dx x, and then ln 2 is constant, so you can keep it aside. So d dy ln y is 1 over y dy dx. d dx of x is 1 times ln 2, which is constant. So you have 1 over 2 dy dx equals 1 times ln 2. So 1 times ln 2 is ln 2. So multiply both sides by y again, by y. So you have this cancels out. So you have dy dx equals y ln 2. And don't forget, y originally is 2 raised power x. So to differentiate y equals 2 raised power x, dy dx will be 2 raised power x ln 2. So that will be original 2 raised power x times ln of 2 at the base. Okay, that's a special case. So let's see if we have another special case. Yeah, this is another special case. I actually did a fast math solution featuring this, so you can check the video out. So here we have y equals x raised power x, and then ln y is ln x raised power x, and then what the reason for the ln is to bring down the power. So we have ln y equals x ln x like this, and take d dx of both sides. So you have d dx of ln y equals d dx of x ln x. So this is looking like product rule now. And then for ln y, you have d dy ln y, dy dx, which we have been doing. d dy of ln y is 1 over y, dy dx. Then this is x ln x, so product rule. So you take x, multiply by the derivative of ln x, then take ln x, multiply by the derivative of x. So you have x here, differentiate ln x, that's 1 over x. Then ln x is here, differentiate x, you get 1. So we try to tidy all that up. So we have 1 over y, this is 1 over y, dy dx, x cancels x, so you have 1. 1 times ln x is ln x. So you can multiply both sides by y, the normal y times, right? Y times that, all this times y, okay? So you have y canceling out here, so that dy dx becomes y into 1 plus ln x. And don't forget, the original y was x raised power x, so you have dy dx equals x raised power x plus into 1 plus ln x, which is the same thing as x raised power x plus x raised to power x ln x. You can have that as another form of expressing that solution. Okay, so that's another special form. So we go to the next slide, should be 46 now. Yeah, now we talk about parametric functions. Parametric functions. These are, I think I showed you graph of parametric functions when we started this whole differentiation, this whole functions of real variables, and it was looking all beautiful, you know. So the idea of parametric function is that, you know, normally you should have y equals f of x. But the interesting thing about parametric function is that both the y, the dependent variable, and the independent variable x are now expressed as the function of another variable, say t or anything you want to call it, maybe t or theta or anything at all. So the independent variable x is a function of t. The the dependent variable y is also a function of the same thing, whether it's t or theta or any other function you want to talk about. And as a result of that, so the derivative is simply going to be dy dt. That if y is equal to f of is a function of t, the dependent variable y is a function of t, and the independent variable x is a function of t also. Then dy dx will simply be dy dt times dy dt divided by dx dt. And the reason for that is, you know, dy dt times, divided by dx dt is the same thing as dy dt times dt dx. So at the end of the day, dt cancels out, so you have dy dx like this. So that's how you deal with parametric functions. So each of the variables, both dependent and independent variables, are expressed as a function of another parameter. That is why they are called parametric functions. Okay, so let's see how that plays out. For instance, find dy dx if y is equal to cos t and x is equal to sine t. So we know that y equals cos t, so dy dt is minus sine t. We know x is sine t, dx dt is cos t. So dy dx is dy dt divided by dx dt. So dy dt, we know dy dt is minus sine t divided by dx dt, we know that's cos t. So you have minus sine t divided by cos t. So that's minus sine t over cos t. Sine over cos is tan, so it means that dy dx in this case is minus tan t. So easy. Just know the rules and apply the rules. That's all about this things. Okay, so we have another parametric expression here. Now, you want to find dy dx if y is equal to square root of p squared plus 1 and x is 1 over square root of p squared plus 1. So again, you have y to be square root of p squared plus 1, which is p squared plus 1 raised to power half. Again, you need dy dp, you know, dy dp, bring down half, bring down the power, differentiate inside, you have 2p, then the other one, you have p squared plus 1 raised per minus 1 half. So 2 cancels out, so you have p into p squared plus 1 raised per minus half. So, and then x, you have x is 1 over square root of p squared plus 1, which is the same thing as p squared plus 1 raised per minus half, because this one is down. So when it goes up, it becomes minus half up there. So the x, the p now will be, bring down the power, that's minus half now, then differentiate inside, that's 2p. The original thing, keep it, that's p squared plus 1 raised power, minus half minus 1, that's minus 3 over 2. If you tidy that up, 2 cancels 2. So you have the minus, this minus, you have it there. This p, you have it into p squared plus 1 raised power minus 3 over 2. So that is us looking for the y dp and the x dp. So we can now go ahead, since we need the y, the x, of course, you know, that will simply be dy dp divided by the x dp, like we know for parametric expressions. So that's what is going to happen exactly. So you have dy dx equals dy dp divided by dx dp. So this is dy dp, which is p into p squared plus 1 raised per minus half, divided by minus p into p squared plus 1 raised per minus 3 over 2. So we can do that. So we have p into p squared plus 1 raised per minus half divided by minus p into p squared plus 1 raised per minus 3 over 2. So, of course, p cancels out p. So we have minus p squared plus 1 raised per, this minus half plus 3 over 2. Minus half plus 3 over 2. LCM is 2. That's minus 1 plus 3. That is 2 over 2. And that is simply 1. That's why you end up having minus p squared plus 1 raised to power 1, which is just that. So that brings us to the end of parametric functions. And of course, I have been flashing you this exercise since you've seen this before for the first set of topics I treated. So let's look at the other assignments in slide 50. Okay, I think I've also shown you this one for product rule and quotient rule. Now, these are for implicit functions. This is for implicit, which I just explained now. Implicit. So find the y dx for x squared y plus xy squared equals x plus y. And then you also have sine x over y minus ln x over y equals y. So try your hands on that for implicit. And then you also have all these other ones. You have find the derivatives. That's logarithmic functions. Now find the derivatives of 1 over root x squared plus 1. Then y equals ln sine x. Then what is the y dx for the following? So you also have some exponential functions here. And you need to find the differential coefficients of the following. Finding differential coefficients is still looking for the y dx. So these are logarithmic expressions. And then you have these ones, parametric expressions. And of course, if you want to plot graphs, like I keep telling you, you can always use Desmos. Then if you can get this textbook for calculus, it's so excellent. And of course, you can always read things up on Wikipedia. And if you have not signed up to my channel, please do that so you don't miss these juicy videos. They promise to make you fall in love with maths like never before. Thank you so much for listening. I'll see you in the next set of videos where I begin to talk about applications of differentiation. So you're going to see practical applications of differentiation in those videos. Bye.